how can universal gravity explain the apple and the moon? So we're going to kind of go into this example that I still have kind of a sketch here of on the whiteboard in a little bit more detail, and recall that we had said this was the Earth, right? This was the moon here, and this was an apple right here. Let's go ahead and look in this slide here, because I've got some maybe another version of this picture here with the moon orbiting the Earth. It's maybe a little bit better than the picture I just had, and the moon's acceleration points towards the Earth. In that sense, what I had drawn over here, you could say, well, this whether it was a force, or you could say it's an acceleration, because if the force points in that direction, or a force applied to that object points in that direction, then that object's going to accelerate in that direction. So that makes sense, right? Now here's an apple tree, and as a joke, I put in this drawn to scale. All my drawings are to scale, right? No, they're not. They're terrible. Anyways, but here's Isaac Newton. He's so tall there that he might be gasping for breath a little bit because his head's almost sticking out of the atmosphere. Anyway, but then there's an apple falling from the tree, and there's the acceleration of the apple. So as we saw before, in this picture, maybe it's a little bit better because I aligned the two of them, so it really clearly shows, because like in this picture you can say, well, they're both accelerating towards the center of the Earth, but in this case, that's the same direction because of their alignment there, right? And it makes sense that the same thing that causes the moon and the apple to accelerate, well, what I mean by that is that it would be the same rule, right? Now, how does this make sense though, right? Because like one of the things that led, I think, Isaac Newton to this insight was the recognition that the moon is orbiting. And an orbit, of course, as shown in this picture, right? An orbit involves kind of a circular motion. Maybe, it doesn't have to be an exact circle, but it could be an ellipse. But it's probably, okay. Pretend it's a circle, and my drawing's not doing it much justice either. But what we know about circular motion is that if there's a velocity, it's tangential to that circle, and if it maintains circular motion, the acceleration must always be at right angles to that velocity, must always be centripetal, must always point towards the center. And if the center of the orbit is the center of the Earth, in that sense, you can really say the apple and the moon are doing the same thing, even though they appear to be so different. But it took, I think, a lot of development of mathematics to understand that connection. One could argue that it's the mathematics of circular motion that kind of led Isaac Newton to his insights. I've made a note here in the slide that the magnitude of the accelerations are not correctly scaled. That is also true in my picture over here. In reality, the moon actually accelerates quite a bit less than the apple would. Well, maybe, I don't know, this apple's kind of far from the Earth, but in reality, if the apple is close to the surface of the Earth, the moon is actually about 60 times farther away from the center of the Earth as the apple is. And that does have an effect when we look at the formula for the law of gravity, for universal gravity that Newton proposes. That will enable us to calculate how those accelerations should more realistically compare than they're shown here.